Hello everyone, my name is Florian Put. I'm a PhD student at Ghent University in Belgium, and today I will present to you the research I did on the development of a stochastic correction factor for the fire load density in a modified Eurocode parametric fire curve approach. So imagine that we want to design a steel column. This column is exposed to fire and loaded with an axial load. We can do it in two ways. Either we do it in a deterministic way. This is quite straightforward, quite simple, but on the other hand, we cannot really quantify the confidence that we have in our design. And the second way is a probabilistic way, which is more difficult, but it does allow us to quantify the confidence that we have in our design. If we want to design in a probabilistic way, we need distributions for both the loads and the resistance of the column. The material properties will definitely have an effect on the resistance part, while everything related to the applied load, such as the magnitude of the load, but also possible eccentricities, will influence the load side. The fire scenario itself, in theory, it can affect both the load and the resistance, but for this particular research, we will focus mainly on the resistance part. If we focus a bit more on the fire scenario, then there are actually multiple ways or multiple models available to represent natural fire exposure. One of the most commonly used methods is, however, the Eurocode parametric fire curve, which takes four input parameters, being the fire load density, the opening factor, the dimensions of the compartment, and also the thermal inertia of the linings. But if we look at the mathematical description as it is written down in Eurocode 1, we can see that there are actually only two main input parameters, being the fire load density and the opening factor. And both of them will have a different effect on the curve that we get. Suppose, in this case, that we have a ventilation controlled fire, then the influence of the fire load density will be that we get a longer duration of the heating phase, and also our rate of decay will change. If we look at the influence of the opening factor, we will see that it changes the intensity of the fire, both during the heating phase and during the decay phase. Now, the problem with such a model is, of course, that we're never really certain about the severity of this fire. Is the severity the same as the severity of the fire that we would expect in reality? And we will demonstrate this with an example. So suppose that we do a large-scale fire experiment and we record the gas temperature curve, so basically with a thermocouple measuring some temperatures inside the compartment. We get a curve that looks, for example, like this one. With this curve, we can start calculating steel temperatures, and this is really calculated, this is not experimentally measured. What we can do is we can develop the Eurocode parametric fire curve that would correspond to this experiment. And we can again calculate the steel temperatures, but then based on this Eurocode parametric fire curve. And what we will see is that in general, the maximum steel temperatures that we get will not be in agreement. And in this particular example, there's a large difference of about 250 degrees Celsius. What we can do in such a case is start modifying the input parameters of the Eurocode parametric fire curve. And we can do two things. We can modify the opening factor, but in this case we will modify the fire load density, which means that we are going to get a longer curve such as this one. So the heating phase takes longer. And we will do it in such a way that the maximum steel temperatures that we get are in agreement, such as in this example. Generally, of course, we will not immediately have the correct correction factor for a particular example, so we would have to use an iterative approach, and that is what is presented here in this flowchart. So imagine that we have some experimental data. We recorded the gas temperature time curve for a particular fire experiment, and we also know the input parameters for the Eurocode parametric fire curve that would correspond to this experimental or to this experiment. So we know the fire load density, the opening factor, the dimensions of the compartment, and the thermal inertia. Then we basically have two time temperature curves. We have the Eurocode parametric fire curve and the experimentally measured gas temperatures. We will then, for both of the curves, calculate the steel temperature, and we will compare the maximum steel temperature that we get from the calculations. In general, these will not be in agreement, which means that we will have to adjust the fire load density that we used in the Eurocode parametric fire curve approach, and we will keep on doing this until we get those maximum steel temperatures to be the same. And we will then say that the correction factor that we need to apply is the ratio of the equivalent fire load density, which is then the fire load density that we need as an input parameter in the Eurocode parametric fire curve to get the same maximum temperature, to the value that was declared from the experiment itself. And if we do this for many different cases, we will get some kind of a distribution for this correction factor, and we basically get a stochastic correction factor. In this case, we did this for 10 experimental data sets, of which the gas temperature time curves are given on the picture here on the right. We looked at section factors ranging from 1 over meter to 250 over meter, and protection thicknesses from 0 to 10 centimeters. So we were considering both unprotected and protected elements. In total, we had 823 cases. Of those 823 cases, 440 were protected and 383 were unprotected. We were initially aiming to have the same number of protected and unprotected cases, but we had to disregard some data for the unprotected ones because we had very high temperatures exceeding 1200 degrees Celsius for the steel temperature, which would mean that the structural relevance would be very low. So that's why we decided to exclude those. Important to note is that we did not use the traditional description of the Eurocode parametric fire curve, because the way it is described in the Eurocode actually introduces discontinuities at the interface between fuel and ventilation controlled fires. Since we are actually relying on the convergence of maximum temperatures, this is something that we cannot have. It would lead to numerical issues. So we decided to use a reformulation that avoids these discontinuities. And this reformulation is given in the paper that's listed at the bottom of this slide. For the results, we will start with the unprotected sections, and we will always discuss the probability density and the cumulative probability density. Now, as you can see from the histogram that we have in the left-hand chart, which is then for the probability density, there's really a lack of clear pattern in the data that we got. This is also indicated by the mean and the standard deviation. The mean is 1.73, the standard deviation is 1.13. And we tried fitting some distributions to this data, but because there's a lack of clear pattern, none of those distributions fit really well. Although if we would consider the cumulative probability density function on the right-hand side here on the plot, the agreement is actually better than we would expect. For the calculation of steel temperatures of unprotected sections, there is one calculation parameter that could influence the result of the correction factor, and this is a section factor. The plot on this slide demonstrates how the value of the correction factor changes with the section factor for different experimental data sets. What we can observe is that for most of the experimental data sets, the influence of the section factor is quite low. We get more or less horizontal lines, except if we go to very low values of the correction factor and for the Ostrava fire test. What is important to note is that the experimental data sets for which we get high values for the correction factor are experimental data sets that declare a high value for the thermal inertia. So this could indicate that the way we consider the thermal inertia in the Eurocode parametric fire curve may not be fully representative of what happens in a real fire. Looking at protected sections, or the results of the protected sections, it is clear that compared to the unprotected sections, we now do have a clear pattern in the results. We have really a peak, and if we try fitting the distributions onto this, we get a very good agreement. The mean of this data set is 1.81, the standard deviation is 0.66, and if you look at the AIC, the Akaike index criterion, which is kind of a relative measure for how well a distribution fits, we can see that the distributions that we tried fitting on there, and we actually tried fitting more than these, but these are really the best fitting ones, are actually very close to each other. Compared to unprotected sections, there is an additional calculation parameter that could influence the value of the correction factor for protected sections. And this is the thickness of the insulation that is applied around the section. If we look at the median values in these box plots, we can observe that these values remain quite constant, although for the section factor you could observe a slight decrease in the median value, although it's not very significant. So overall, the influence of the installation thickness and the section factor is quite low. What is important to realize is that the outliers originate again from the same data sets, which indicates that the data set itself appears to be more important, and well, not really the data set itself, but mainly how it relates to the input parameters that are declared for the Eurocode parametric fire curve. For convenience, we decided to combine the datasets for protected and unprotected sections into a single dataset so that later on we can use one stochastic correction factor in an application example. And we found that by combining those datasets, we now have a mean of 1.77 and a standard deviation of 0.91. Looking at the AIC values of the distributions that we tried fitting on this data set, we can see that the Birnbaum-Sanders, the log normal, and the inverse Gauss distributions have fit similar. There's not really a clear winner because we have a slightly lower AIC value for the Birnbaum-Sanders model. We decided to use this one, but of course, slightly changing the data set, adding more points could actually lead to the inverse Gauss distribution or log normal distribution to be a better fit. But for this case, we decided to use the Birnbaum-Sanders model. Important to realize is that the introduction of a stochastic correction factor is only relevant if the inclusion also has a structural effect. And to have a structural effect, there are certain thresholds for the temperature that we need to exceed. If we look at the Eurocode 3 model, we will get a yield strength reduction from 300 degrees Celsius onwards, while an elastic modulus reduction will only happen from a temperature of 400 degrees Celsius onwards. The histogram displayed on the slide is demonstrating how the maximum steel temperatures that we got from the previous calculations where we determined the stochastic correction factor relate to these thresholds. Focusing on the blue histogram, which is for the protected sections, we can see that in many cases we actually remain below these thresholds, meaning that in these cases we do not expect a significant influence by introducing the stochastic correction factor. But if we focus on the unprotected sections, which is then the green histogram, we can see that the vast majority of these cases exceed these thresholds. So we actually expect a very large influence for the unprotected sections. With this information, we can go to an application example. So suppose that we have a column which is 3 meters tall. The column is actually loaded and is simply supported. The section of this column is an HEA 200 profile, which is an I profile, and it is exposed to fire from 4 sides. We're considering both a protected and an unprotected column, and in case it is protected, we would have 20 millimeters of sprayed fire resistance material as protection, and based on a calculation, this would amount to about 90 minutes of fire resistance. We will do a probabilistic analysis based on 10 to the power 5 realizations, and the stochastic correction factors that we used can be found in this table. What I want to highlight here is that now we have two stochastic variables for the fire load density. We have the normal fire load density. So imagine that we have 2 offices, then not both offices will have exactly the same fire load density. So that's what we take into account with the stochastic variable for the fire load density. But now we also have a correction factor for the fire load density, the Birnbaum-Sanders model, with a mean value of 1.77 and a standard deviation of 0.91. And this, of course, corresponds to the combined data set for the protected and unprotected sections. We are considering 2 failure modes for this column. We have yielding, meaning that the stress due to the applied load would be higher than the yield strength at a certain temperature. And we have global buckling, which is a second order effect, and is mainly related to the geometry of the section and the elastic modulus. For the results of the application example, we will distinguish between the results for the protected sections and the results for the unprotected sections. If we focus on the critical resistance for protected sections, we can see that the introduction of the stochastic correction factor, so by going from the blue histogram to the green histogram, does not have a significant effect on the critical resistance of our column, because what we observe are just two lines over here, and those lines are mainly overlapping. And to explain this, we need to take a look at the maximum steel temperatures reached. So again, we start from the blue histogram, which is for the normal fire load density, and we go to the green histogram, which is the corrected fire load density. And we can observe a decrease in the peak, and we can also see that our distribution basically gets shifted to the right. So we definitely have a temperature effect, but because the maximum temperatures in the vast majority of the cases do not exceed the thresholds for material property reduction, this is not reflected in the critical resistance of the column. If we take a look at the unprotected sections, the critical resistance of the column is definitely affected. And again, to explain this, we go to the temperatures. So what's happening qualitatively is the same as for the protected sections. We get a lower peak and the distribution gets shifted to the right. But now we have many cases with maximum steel temperatures exceeding the thresholds for material property reduction. And so we can say that the critical resistance will be affected. And with this, we can start drawing conclusions from the research. We can say that we developed a model uncertainty for the Eurocode parametric fire curve model by considering a correction factor for the fire load density. This correction factor basically lumps the uncertainties related to all calculation parameters into a single correction factor. We did not do this for the real Eurocode parametric fire curve, but rather for a reformulation that avoids the discontinuities between fuel and ventilation controlled fires, as it is introduced by the traditional description of the Eurocode parametric fire curve. Based on the current data sets, we can say that the thermal inertia is an important parameter for the value of the correction factor, and that the section factor and protection thicknesses did not have a significant impact. And lastly, we can say that mainly unprotected elements are affected, but that's only the result of a single case study. If we would have a different case study with a much longer fire exposure, then the temperatures inside protected elements can also get much higher, and they may actually pass the thresholds for material property reduction. So this is really case study dependent. All that's left for me to do now is to thank you for your attention and to thank you for watching this presentation. In case you would have any questions related to the research I presented in this presentation, you can always contact me through the email address that's listed on the slide here.